and has done a lot of work in transfer learning and multitask learning, which I think is incredibly relevant for this workshop on learning from multiple heterogeneous sources of data. So really excited to hear from you. Thanks, Samory.
Thank you. So I have about 40 minutes, or yeah? Okay. Hi everyone. So I just want to talk about multitask learning. Here I mean multitask learning very generically. You can call it multi-source learning, etc. It just, the whole point is that you have a lot of data from multiple distributions, and you want to do well with respect to one distribution. So the talk will be based on two pieces of work, one with Steve Haneke and another with Arthur Gretton, Dimitri Meunier, and Zuli. All right, so first thing, for those who don't know Arthur and Steve Haneke, that's Steve on the, is that right or left? Right. And this is Arthur, right? And both are great researchers that I've had a chance to really interact with. And so, I saw them at the NeurIPS just a few months ago. All right, so what is the talk on? Modern classification or regression. We often, and I don't need to convince anyone here, we often now augment perfect data with related imperfect data. And that's the whole point. And medical applications, all sort of applications where you just don't have enough good data, enough perfect data, and you need to take into account a lot of other data from other sources that you hope are related somehow, and you hope will help you improve regression or classification on your target task. So throughout, I'm going to just assume that all the data sets that you have are labeled. So it's only prediction problems. All the data sets that you have are labeled. You want to estimate some unknown function fq of x. And q here will represent throughout the target problem I'm caring about. And please feel free to interrupt me anytime. So multitask will just be viewed this way. I have an f hat, which is a learner, any learner, that has access to P1 through P begin, each contributing sample size small n. And we want to do well on Q. So for the sake of presentation, I'm just assuming that the sample size from each task is small n is the same. In the results that we have, we cover any number of samples. So the performance measure is this excess risk defined over some loss. I'm going to be generic for now. It's just an excess risk over the best risk in some given class F. So we fix a model class, and we want to do as well, we want to compete with the best risk under Q, under the target, over the class F. And we want to understand this as a function of small n and big N. That's the key point. How does this behave as a function of small n and big N? And in particular, the question we're asking is this. Under what conditions is it that multitask learning would guarantee a gain over single task?
So Q can, of course, be a very different distribution, but this also allows like mixtures of people.
Well, I'll give exact definitions, okay? So I'm just giving high level what the problem is. Well, what is the promise of multitask? Everybody understand that the promise of multitask is that I'm assuming here also that I have n data points from Q. The promise of multitask is that my rate of convergence is going to be faster than a rate of convergence just in terms of little n. Fine? And that's the question being asked. When is that promise fulfilled? Clear to everybody? For instance, if all the P1 through Pn are extremely close to Q, we can imagine that, yes, I should have a rate of convergence in terms of small n and big N. If all the P's are very far from Q, then that might not happen. In particular, if the P's give me a completely different, let's say, regression, then it could actually hurt to use the piece. Fine? And so there will be a couple questions here, not just understanding these rates of convergence, but also understanding which algorithms are capable of achieving them without knowing a priori the relationship between the P's and the Q's. Here, the baseline that I'm going to use every time will be the best possible rates of convergence that can be guaranteed under the target data alone. Clear, everyone? And can I beat it? And for simplicity, I'm just going to write it as epsilon q of n, where script q is the class of distributions I'm allowing myself to assume under q. Clear? There was a question?
You just answered it. It was about the baseline.
Okay. And so the basic question, which settings, under which settings, what procedures, and what information on the relationship between P's and Q do the procedures need to have in order to ensure the promise of multitask learning? Clear, everybody? All right. So the main message is that the picture is actually quite mixed with negative and positive results. There will be some situations where we would expect that we should be able to gain from multitask, but we are not able to gain from multitask, provably. And there will be situations where, if we relax things further, we are able to gain from multitask. Let me actually step back for a second. The philosophy of this line of work is the following. Negative result, for me, serve a purpose. It tells me what sort of information does an algorithm need to have in order to do well. And a negative result says, without this type of information, we just cannot accomplish what we want to accomplish. And so that's the whole point of trying to study this type of negative result. So there'll be two ways. Obviously, all these results will have to depend on how we relate P to Q. The P's to Q. There'll be two ways, unstructured and structured. By unstructured, and this is, I'm using these words colloquially, it's not formal. Unstructured just means that we make usual assumptions of considering distributions between, distances between the distributions P's and Q. Distance is viewed informally. It could be total variation, KL divergence, all these notions that have appeared in the literature on relating P's to Q. And I consider that unstructured. Fine? And then the structured setting is we have some type of latent representation that is shared between P and Q. All right, so those are the two types of settings we'll consider. And the unstructured classification setting, for the unstructured setting, I'll mostly consider classification. It's what I'll talk to you about is based on joint work with Steve. And the mixed picture just essentially says that sometimes it is possible, and then impossible in general, even when the P's appear very close to Q. And I'll make it clear what I mean by the P's appear very close to Q. And the structural regression setting, this is work with Arthur Grayton et al. And we'll show that it's often possible if the assumption holds that there is some shared structure, substructure between P and Q. Usually, the shared substructure is some representation of the data. That representation is shared. Then it is possible, but with smaller gains that we might hope for. And I'll make that clear also. All right. Any question as to the settings?
So just like one comment on the setting.
Yeah.
So here the view of multitask is somehow you have capital N tasks and this Q and you want to improve on Q.
Yeah.
And this to me seems, okay, sometimes harder but sometimes easier than the following problem where I have all these N+1 tasks and I actually care about some average notion of performance over all N+1 of them.
Yeah. So I'm not talking about an average notion. I'm just saying if I'm caring about doing well on, imagine the case where I'm caring about doing as well as possible on each one of my tasks.
Right.
This falls under this too.
Because you can set Q
You can set that to your target.
Okay.
Clear?
Yeah.
All right. So for me, that's why multitask, multi-source, I view them as the same problem, because eventually, usually I'm not caring to do as well as possible with respect to the average of the task, because that to me is just a surrogate for what we're really caring about, doing as well as possible on every task.
Right, but then if I set Q to be one of these distributions, then somehow I will, of course, do better. There's an algorithm which just ignores all n-1 things.
No, the whole question is, can I do as well as the combination of all the data sets? Let's go back to the main question. The main question is this. Can I beat what I can do using the Q data alone?
Right.
That's the question.
Right. Yeah, I understand, but like Q can be anything so far.
Q can be anything
right,
so far.
so-
Your questions, I think, will be answered as I
Okay,
keep
okay.
going. Fine. All right. So again, I'm asking, does the promise of multitask hold? Can I get a rate of convergence that is in terms of all the data that I have, that I'm observing? Including the Q data. Q also, I'm just assuming Q also has data. I have data from Q. I can decide to ignore the source or use the source. Fine. All right. So let's start with the unstructured setting. If your question is not answered, please let's get back to it. So let's start with the unstructured setting. So what I'll do in the unstructured setting is I'm just going to consider the parametric version of this problem. So F is a VC class. For VC class here, for those who don't know, I'm sure most everybody knows VC dimension. For those who don't know, all I'm doing is controlling the complexity of the class. Fine. So I'm assuming a fixed VC class, and the risk measure is just the misclassification error. The single task rate, in this case that I'm competing with, is of the form D over N, 1 over 2 minus beta. Beta is a noise measure. Fine. I'll explain it more in a second. D is the VC dimension of the class. So that's the minimax rate of using just the target data. Fine. And sorry, the beta is to capture the intuition of easy to hard classification problems. It will turn out that how well I can do in multitask will depend on the beta also. Fine. And so for now, I won't quite define it, but just imagine that the beta is one that's low noise conditions. That will be, we have margin around the decision boundary. And the beta is 0 is the general case. That's when you get a rate of the form 1 over square root n. So single task rate is just really an interpolation between a rate of the form, a fast rate of the form 1 over n, and a rate of the form 1 over square root n. And the beta captures where you are on this continuum. So this is called a Bernstein class condition. You don't have to worry about the definition. The definition is here. Just whenever you see the beta, it's how hard the classification problem is. Fine. All right. So the question then is there an F hat, a learner that can achieve a rate faster than this? And it seems that there should be, but here I'll make it clear why we're asking this question, because we first took a look at a lot of theory papers on the subject. And usually, the rate of convergence you get is a rate of the form for their favorite algorithm. It's a rate of the form, something that goes down with total sample size, little n times big N, plus a term that just depends on little n. Fine? And so this is the worst term. And so it almost suggests that you cannot do better than using just the target task up to constant. And that to us was surprising. Luckily, this is an upper bound. Maybe it just means that these analyses were not tight. Or maybe these algorithms are not able to achieve better. Fine? But here's the question. Can we do better? So it turns out that the picture is quite nuanced in the following sense. I'll show you just a simple situation, an idealized situation, where an oracle should be able to achieve a rate of convergence in terms of aggregate sample size, not necessarily little n times big N, but an aggregate sample size So definitely a rate of convergence much faster than in terms of single task. Yet, no algorithm exists that can achieve that rate without knowledge that the oracle has. I hope that's clear. The high level? Fine. All right, so here's the formalism. First, I need to formalize the relation between PTs and Q. And the way we're going to formalize that is just sort of assuming, or just using this basic intuition as to why am I using the source data anyway. I'm using the source data sort of because I believe that if I have a classifier that has low error under the source, this classifier should do somewhat well under the target. Fine? And so that's the basic sort of intuition we are going to try to formalize. Low error under the source, any classifier with low error under the source likely has low error under the target. How low is what we're going to parameterize. So next thing is we're going to make the problem easy so that at least an oracle should be able to achieve a rate that is faster than single source rate. So let's assume that all the F stars, all the best classifiers for every source is equal to the best classifier for the target. Fine? So intuitively, it feels like this should be an easy problem. It feels like this should be an easy problem, and what we'll try to show is that yes, for an oracle, it will be an easy problem. But we have to take into account sample size. We have to take into account the fact that we have finite sample, right? If an oracle knows has enough samples to achieve the FT star, it's done. But we have finite sample, and so because of finite sample, it will turn out that there is some hard problems embedded in multitask that would not allow an adaptive procedure to actually adapt to the best possible rates achievable by the oracle.
So here we're assuming that there exists at least one function for each task which is the same, not all optimal functions for each task.
I'm going to make it easy. Every task has a single
So
optimal
a
function.
unique,
Yeah,
okay.
make it easy. Right. Because the whole point is I'm going to try to give you a negative result. So it makes it even harder to give you a negative result by making the problem easy. Fine? So now this intuition, the way we formalize it is actually simple. We're just going to say that it's actually very direct. We're just going to say that driving down the error on the source implies driving down the error under the target at some rate that depends on some unknown rho t, right? At a polynomial rate depending on some unknown rho t. So it's just one possible way to formalize this. Clear, everyone? It's just a parameterization of the problem. So let me see, before I even go further, let me actually just give you this here. Even though it's a specific parameterization of the problem, you can show that the various notions of distance that people have proposed in the literature really just boil down to this, to saying that as I drive down source error, I'm driving down target error. Because this is essentially a modulus of continuity between the two excess risks. How fast does target error go down as source error go down? And it turns out that under the various assumptions that people have made in the literature, this is all they're trying to bound. And you can recover a lot of the existing rates by just using this type of parameterization of the problem. Is that clear to everybody? So it's without loss of generality. It's without too much loss of generality, but let's try to understand what the polynomial form means. When I say you can recover, not necessarily the polynomial form, but some function of the other. Fine? So let's understand what the polynomial form means. So here, suppose the case rho is equal to 1 is actually easy to see. Suppose that I have Q is uniform and that X is just the line. I don't know if you can see. Yeah, so post Q is uniform, X is just the line, and P is also uniform. F star is the decision boundary here, right, for my problem, so it just thresholds on the line. F star is the decision boundary. If I'm trying to understand the excess risk between an F and an F star, I just have to measure this area where they disagree. Fine? And that tells me that the excess risk on the P or on the Q are just constant away from each other. So rho is 1. The squiggle just means up to constant. Clear, everyone? So this will be a case where rho is equal to 1, which would mean that I can treat the source and the target almost the same. This will be a case where rho is large. The intuition is just that P now gives very little mass to the decision boundary compared to Q. Rho is large. That will mean the P is very far from Q, the larger rho is. So that's the intuition. Every time you see large rho, P is far from Q, small rho equal to 1, P is close to Q. Clear? There could still be a distribution shift, but the distribution shift only changes the rate up to constant. So that's all this parameterization is capturing. All right, so let me move further. So what is the minimax rate for the setting? So the minimax rate for the setting looks like this. I'll explain it. So now we assume that every PT is some distance, quote unquote distance, rho t from Q, from the target. All the F stars are the same. It turns out, when I say minimax rate, that's the rate achievable by an oracle. An oracle that knows the rho t's. Fine? So an oracle that knows the rho t achieves a minimax rate of this form. It's not a closed form, but we can characterize the minimax rate this way. What is the characterization? It says that, by the way, this is up to log terms. That's the minimax rate. It says that take any PT and look at and rank them, the ones that are closest to the target and from closest to farthest in terms of rho t. Fine? And the minimax rate is just an aggregate of the closest to the target up to this rho bar t, which is the average of the rho t's. And that's all this is saying. There is some cutoff, and the cutoff depends on the actual value of the rho t's and t times n. Clear, everyone? The main point is that this, in most cases, if you just have a lot of very good sources and a lot of very bad sources, then it's an aggregate of the very good sources. The number of very good sources times n. That's all it's saying. Is that clear, everyone? So for nice rho, the oracle can achieve a rate of convergence much faster than single task rate of convergence. However, even when rho is admissible in this sense, no practical, no algorithm, no practical F hat, and by practical F hat, I mean adaptive F hat, one that does not know the rows, can achieve a rate actually better than single task rate. So that's the main result. And I'll give you an intuition as to why in a second. Fine? So,
I missed the definition of the rho.
So rho is just measuring how fast driving down error under the source drives down error under the target. Right? And so it's just a way to unify various notions of distance between source and target. You can imagine if source and target are very close on the total variation, the rho should be small. Or KL divergence and such, and in fact, you can show it. It's easy to show. Clear, everyone? All right. So, all right. So the construction idea is the following. So how you show this impossibility result? The construction idea is the following. We're going to construct a situation where, suppose there is big M, sources that are good, and good in the sense that rho t is equal to 1, but much less than the big M. Okay? But enough so that we already know that we will achieve a rate much smaller than single single source rate. And then there are many bad ones. Fine. The good ones are interspersed between the bad ones. Is that clear to everybody? And so if I know the positions, that's what the Oracle does. The Oracle knows the positions. It can just pick the good ones, combine them, aggregate them, and use them as a replacement for the target. Clear? However, the adaptive procedure has to find which ones are good, which ones are bad. Okay? The other thing that we do is we need to make little n small enough. So what do we mean by bad? Little n itself should be small enough with respect to the rows and the noise in the problem to be able to switch the identity of H star, of F star. Fine? Now, in all of these guys, the identity is switched. If you don't find the good ones, you necessarily incur a large error. And only those algorithms that just give up and rely on the target data can get the rate, this rate. Fine? So that's the main idea. You randomize now over all possible values of M, all possible positions. So that's how you mimic the algorithm not knowing a priori how many good sources there are and how good they are. Is that clear?
Sorry, just to clarify, so in the previous slide, I thought that you were doing a worst case over rows, so you don't know the row, or like, so in that sigma of rho and B.
So here, I know the rows. And now, to understand a practical algorithm, the practical algorithm does not know the row. So I have to randomize over all of that. Is that clear? And so that's how the construction is there are very good rows, there are very bad ones, but the algorithm does not know which position. And in order to solve for the good ones, it has to do, this is informal, it has to do so many hypothesis tests, and how many is 2 to the O of n. Those who know multiple hypothesis testing know that the cost to the rate will be log of this, so it's big N times whatever rate you can achieve. That's why you can never achieve a rate better than 1 over n. So that's the high level of it. So it's a reduction, the whole analysis is a reduction to multiple hypothesis testing that just makes it impossible, even though an oracle can achieve a fast rate, makes it impossible for an algorithm that did not know the positions to achieve a fast rate. I hope that's somewhat clear, the high level, please.
Construction was for a specific multi-set of the rows. It's an instance-wide version of the...
See, repeat? Sorry.
The construction was for a specific multi-set of the rows. Is it an instance-wide result that applies to any multi-set of the rows?
No. Yeah. I mean, here is how, it's not a specific one. We can make it for different values. The key ideas are that there are good ones and very bad ones. That's the whole key idea. And that little n, the number of samples per, is set so that you just cannot identify from a single, you cannot identify from the bad ones what H star is. That's all. That's the main ingredient, so you can construct that for various values of rho, if that's sort of the question you're asking. Right. Here I'm giving you an intuition, rho is equal to 1 as the good value of rho.
So can I view the n small enough also as maybe a condition that, oh, this is actually how the rho t and beta should behave, so that I can run the hypothesis test and using the finite sample somehow?
I'm not sure I understand the question, but let me answer a similar question in a second. Fine. Again, let me go back to one thing I said earlier. One thing I said earlier is that this type of results really just tell you it's a way to try to understand what an algorithm needs as information in order to achieve a particular rate. And we're just saying that without this type of information, there is no algorithm that can achieve a rate that guarantees actual multitask. Is that sort of clear? That's the point. However, there is tons of conditions here, and that's there's tons of conditions here. What remains open is what are sufficient enough conditions. We know some, But can we make the sufficient conditions for multitask to be guaranteed? Can we make them tight? That we don't know. We just know that under these various conditions, it just cannot be guaranteed. And under some other very favorable conditions, it can be guaranteed. There is a gap between all of those. Okay? All right, so let me give you actually some few conditions. Suppose I know a ranking. If I know a ranking, I just know only which rows, which tasks are closest to the target. That's enough to achieve nearly the minimax rate. There exists an adaptive procedure that can use this information of ranking or approximate ranking in order to achieve the rate. Fine, everyone? On no noise condition, a low noise condition, if beta is equal to 1, so if the classification task itself was easy, then, in fact, it breaks the construction. If the classification task is easy, then I cannot force the bad task to flip H star easily. So in this case here again, you can be adaptive. If there is margin, you can be adaptive. If there is enough margin, you can be adaptive. Just combine all the data because all the H star, all the F stars are the same. Combine all the data and just take the best there. It will do well. So that's the high level. And there are many other cases we considered, many other procedures we considered in the main paper. Okay. So the main question here is now for tightness. This allows for regimes of these parameters of sample size n, big N, distances, and all that, under which we still can do multitask. This remains open. What are the exact regimes? What are the tight regimes under which we can do multitask remains open. The key message is simply that there is no gain over a single task if you don't assume anything. Right? Even if you assume that all the F stars are the same, that's not enough. That's the point here. In the non-parametric setting, we have more of a complete picture in some other papers of mine. So I'll leave the multitask, I'll leave the non-parametric setting out, but whoever wants to discuss it, I'm happy to discuss it. Okay. So there we have a very tight picture. All right. So structure regression setting. According to my thing, I have about 10, 12 minutes. Yeah?
You can go look.
Okay. So the structured setting, let's talk quickly about the structured setting. Here we have good news, right? We have good news. We've assumed enough about the relationship between the PTs in order to gain. So let me remind you quickly what's been assumed. So here in regression, I'm going to assume, I'm just going to consider least square risk. And the general assumption is that there is some, the source task and the target task only differ through some link function. And there is some shared representation that is the same. So first, the linear case. The linear case, I'll use the linear case for intuition. The linear case has been considered quite a lot in the literature on the subject. There were some initial papers by Simon Du, Jason Lee, Sham Kakade, etc., and that has just given rise to a lot of papers on the linear case. Fine. So the linear case is simple. P is a low-dimensional projection. That's the shared representation. V is this unknown regression function. And what we considered in our paper is the nonlinear extension, so the nonlinear case. Why the nonlinear case? I'll give you first intuition from the linear case, and then show you what breaks in the nonlinear case. But why do we want to consider the nonlinear case? Because, I mean, in the end, the whole reason we're doing this is to try to understand neural networks to some extent. Right, so that's, so the linear case is the first good step, but the nonlinear case actually starts showing us certain things that the linear case just cannot show you. And I'll make that clear in a minute. Okay, so intuition from the linear case. Let me try to go through this without flying through it. The intuition is very basic. P is a low-dimensional projection, let's say of dimension S, much smaller than D. So if I knew the subspace V onto which P projects, if I knew the subspace V, then I can just do regression in that subspace, and I get a rate of convergence S over N much smaller than D over N. So that's all. right? So the whole point is use the end sources to learn a v hat that approximates v. And if v hat approximates v enough in sin theta error is just the angle between subspaces. If it approximates enough in sin theta error, then I get this rate, which is much better than single task rate. Fine? So the whole point now is to understand how do we get the sin theta error small enough using all the aggregate of all the tasks. So richness assumption, usual in these things, is that the VTs, we can assume without loss of generality that each one of the VTs, the regression vectors, are in the subspace V. Fine? It's equivalent. So we can assume it's in the subspace V, and the richness assumption is that they span the subspace. That the sources are rich enough that the VTs span the subspace that I'm after. That's all. Fine? Then I can look at the covariance between the VTs, not quite a covariance, but this average outer product between the VTs, and the range of this sigma is V, right? So since the range of this sigma is V, I can just estimate sigma by sigma hat, where sigma hat does regression in every task, fine, and then take the range of that sigma hat. Clear, everyone? So that's the main assumption in the basic linear case. And when I say linear case, the RKHS case is also linear, but it's infinite dimensional linear, right? So that's the way to view it. It's linear through a nonlinearity. So, which sounds funny if you say it that way. So we want to estimate this V through a V hat. And then the analysis is actually simple. We want to analyze the sin theta. Sin theta between V hat and V can be upper bounded by the operator, the estimation error in an operator norm. And this is just really a perturbation analysis. It's not really estimation, right? It's just a perturbation analysis. And the key thing we're using here is really, in fact, that, yeah, so don't worry about it for now. This is just a perturbation analysis. And then what is the rate here? The rate here will be in terms of, this is purely a variance term because sigma hat is an unbiased estimator of sigma. And so because it's purely a variance term, I just have to upper bound the variance, and the variance is upper bounded by the single regression estimation error. And now you get a rate of convergence of this type that integrates the total sample size. Clear? So that's the general analysis. All right, so now you just need, obviously, big N and small n, now small enough to get the rate smaller than single task rate. So that's the whole point of this analysis. Now, let's go to the nonlinear case. F is now in an infinite dimensional RKHS. The key point is that F is that the model class is infinite dimensional. Fine. If the model class is infinite dimensional, again, we're going to do the same, we're going to use the same idea. We take the outer product of the regression functions with respect to the inner product in the RKHS, and then we estimate this operator this way through regression. However, now, because we're in infinite dimensional space, the regression has to be regularized. Clear, everyone? And that's the key point. You have to regularize the regression, otherwise you just cannot do regression in an infinite dimensional space. But now, the F hat T's are now biased. Is that clear? And because they are biased, when you try to analyze the sin theta, you have a bias term that comes in, and bias just cannot be aggregated out. Right? You cannot average out bias. In the linear case, what you were able to do was you were able to just get an unbiased estimator, and so you only had variance noise to average out. Now you don't have noise alone. You have a bias term that depends on this regularization parameter lambda. And your variance of these regularized estimators is also depending on lambda, and so you have to do a trade-off on these two terms. What it turns out is that the right trade-off forces you to overfit every regression. Is that sort of clear? The choice of lambda is no longer the optimal regression choice of lambda in order to get the bias down appropriately and gain from these parts of the terms. So that's the key point, is that now you have to overfit. Yeah, you have to overfit. And then there is another problem. There is a deeper, more nuanced problem here, and I'll try to explain it. If I have 2 minutes? Okay. So here's the more nuanced problem. The more nuanced problem is the fact that you need to understand this regression in the RKHS norm, as opposed to understanding the regression in L2 norm. Is that point clear? I have to understand the regression in RKHS norm as opposed to in L2 norm. What the main problem is, for those who are familiar with our RKHS theory, the entropy numbers are ill-behaved in RKHS norm. You're in an infinite dimensional space. If you take a ball in the infinite dimensional space, that ball is non-compact. So covering numbers are not well behaved with respect to the metric in the space. The beauty of RKHS theory is that you are in an infinite dimensional space. Your balls are not compact. However, you are not looking at the ball from the point of view of the norm on that space, but from the point of view of the L2 norm. That's what makes regression possible. Now, all of a sudden, I have to look at it from the point of view of the norm in that space. And what that forces me to do is that I have to assume a lot more regularity on the regression functions themselves. The regression functions themselves need to lie in a small part of that space. So without those conditions, we cannot gain. We cannot even get a nice bound of this form that doesn't blow up. So all of a sudden, we need a lot more conditions for multitask to succeed the moment we go away from the finite dimensional linear case to a nonlinear case, which we hope is telling us a bit more, getting us closer to what we may observe with neural networks which are nonlinear. For instance, the fact that you need to overfit your regression in every subtask. All right. So I'll stop there. The main theorem is that under all these conditions, you again can get a rate that is much faster than the single task rate, but under additional conditions that further smoothness on the problem than might be true in the linear case. Optimality of the rate remain open. We don't even know what the optimal rate is for the finite dimensional linear case. We're hoping that we should be able to get a sense of it soon. But when I say we, I don't mean me. The community does not know what the minimax rates are for even the linear case. All right, so I'll stop there. Multitask, there is a mixed picture. There is a mixed picture with positive and negative results, which just tells me that we still don't understand much about the problem itself, at least on the theoretical side. So, all right, that's all. Thank you.
Questions for Samory? I got a lot of questions here. That's all. Yeah.
So, can your negative result in the first part be extended to maybe something of the following flavor? So, there exists k, let's say order capital N by 2, such that there doesn't exist any adaptive algorithm, such that all i's which are, let's say, like basically some subset of all the P1 to PTs, and I'm looking at all adaptive algorithms, and I want to show that there doesn't exist any there doesn't exist any adaptive algorithm such that it can be better than just individual training on all of them. So there doesn't exist like a non-trivial fraction of my actual P1 to Pn task, such that the kind of result you show would also hold for on all of them simultaneously. Because here, the samples in Q seems to be like the bottleneck to do the hypothesis testing, if I'm not wrong, if I understood correctly. The sample size of Q, the samples you get from Q, and small n is the same, and that was the bottleneck to do the row estimation correctly from the finite samples, or no?
I guess I'm not sure I understand the question. There is no, you cannot estimate rho. Rho is with respect to the unknown regression function.
So, okay, my question is there a hard instance on which you can show that there's no non-trivial subset of all the capital N tasks on which you can simultaneously not improve.
On which you cannot.
Simultaneously not improve compared to the non-collaborative rate on each of those tasks.
I'm not sure what the collaborative rate means.
Non-collaborative rate means just
Maybe you
the
can ask me
epsilon
offline. I don't-
big Q thing that you had, where big Q is replaced by
The
PS.
worst case rates?
Yeah.
I mean,
P over N, 1 over 2.
the construction is over big N tasks, right?
Yes.
I can take any subset and make that same construction there. I'm not sure if I understand the question.
But can you use the same construction such that it holds for multiple?
The key idea of the construction is that in order for an algorithm to identify the good tasks,
Yes.
if the two things. One, if the algorithm doesn't understand the good task, it has to do bad.
Right.
Fine. In order for the algorithm to understand, identify the good task, it has to solve, it has to look at all possible subset almost, right, of the big N. And that's too many hypothesis tests to solve in order to identify the good task. If you identify the good task, you are done. You can get a fast enough rate. But we make the problem hard enough to be able to identify the good task.
So can you use one hard instance to show that this identification is hard for all tasks P1 to N, if I'm varying my Q from 1 to N basically?
If I'm varying my Q from 1 to N.
Like I'm just trying to understand, is there any is it saying that there's no benefit to collaboration, like when your Q is somehow arbitrary, or is it also saying something stronger that even if you look at all sort of mixtures of your P1s to Ns,
Let's put it this way. When I say there is no algorithm, I mean pick your favorite algorithm. The algorithm can take a mixture. Your algorithm can try to estimate. Your algorithm can try to do anything.
yeah.
It's just not going to do better than this rate. It cannot guarantee a rate better than this rate.
Okay, maybe I'll talk to you offline.
Okay. So that's the high level. It's just like it's an information theoretic impossibility result.
Yeah, I understand the
Right,
result.
yeah.
I'm just trying. I'm not sure. Maybe my question is.
Yeah, maybe offline it might
Yeah.
be more easier for me to understand. Yeah.
Yeah.
Okay.
All right, let's thank our speaker again. So we'll be back at 10:45 for the next talk. We have a short break.